recording. Okay, so there are two functions, left and right here, and it says both of them are increasing, which is true, right? They're both going up forever, going up forever. We're going to assume that this won't curve downward at any point. It is increasing, just flattening out a little. This one, of course, is increasing differently. They are different. They're both increasing. If you were to take slopes of at any point on these things, here, let me just use a different color than black for a change. Right, the slope here would be lower than it is here, would be higher and higher. Notice the slopes, that last one's absolutely terrible as a slope, but you get the idea. The slopes here are increasing, whereas the slopes here are getting flatter and flatter, they are decreasing. So that's one of the things that's different about them. Those of you who come to me from a physics background, you would say, well, okay, if this was my distance versus time graph, this one, the speed is increasing, this one, the speed is increasing, but this one, the acceleration is decreasing, and on this one, the acceleration, or sorry, let me say that again. On this one, the acceleration is increasing, and on this one, the acceleration is decreasing. Similarly, here's a couple of decreasing functions. Notice that on this one, again, the slopes start out very steep, but are flattening out, whereas here they start out flatter and then get steeper. So in general, we would say that a function is called concave up over an interval if the graph of the function is above the tangent line at each point of the interval. So let me go back to those tangent lines I drew. I don't know why I erased these guys. Oh, because they were terrible, that's probably why. So there we go. Notice that except for this one that I drew really, really badly. Let me try that one again. There we go. All of the tangents here are below, and all of these tangents are above. All of these tangents are below, all of these tangents are above. So in general, a function is concave up if the graph of the function is above the tangent at each point. A function is said to be concave down on an interval if the graph of the function is below the tangent. So now looking at all four of them, notice these two guys have something in common with each other, and these two guys have something in common with each other. We would call these two guys concave up, we'd call these two guys concave, or we'd call these two guys, we'd call this concave up, and we'd call this concave down. So there we go, concave up, concave down. Here's a nice little chart that summarizes the characteristics of these things. So on this guy here, we'd call that concave up. The function itself is increasing. Its derivative would always be positive because it's increasing in its slope as you go. And since the slope is increasing, the derivative of the derivative would be positive. Now this guy is also an increasing function, so its slope is positive, but it's concave down, which means that its slope is getting smaller the further you go, which would mean that the slope of the slope would turn out negative. For my two decreasing functions, this one, of course, has the change in the function is negative, the change of the function here is negative. But I'd call this one concave up, just like the one above it, because as the slopes are changing, they're changing in an increasing way. So f prime primed is positive, whereas here, f prime primed is negative, right? This is getting to be a less and less negative slope as you move along. This is getting to be a more and more negative slope as you move along. So the second derivative here would be positive, the second derivative here would be negative. Okay, so that probably gives you a pretty good hint as to where this is going. To test for concavity, how concave a function is, for a function f of x with derivatives f primed and f prime primed on an interval, the following holds. The function is concave up when the first derivative is increasing and the second derivative is positive. A function is concave down if the first derivative is decreasing and the second derivative is negative. So looking at just kind of an everyday curve here, concave down again is kind of a curve going that way. It's going to have, of course, a local maximum. Concave up is going to have a local minimum, and we'd call that point B, that's a B, the inflection point, or the point of inflection. I usually call it POI for point of inflection. Okay. On diagrams, it's usually pretty easy to tell. Determine where the curve is concave up, concave down, and where the points of inflection are. So where does it change from a curve that's going to have a minimum to a curve that's going to have a maximum? And it looks like that's going to happen at point P. So I'm going to say that we are concave up. That's supposed to say up. Fix that. Concave up for the intervals from -4 to 1. And then we're concave down until we get to the 3. So then from 3 to 6. And then from 6 to 8. All of those are concave up. They all are intervals that have local minimums. Concave down intervals would be from P to Q, so that would be from P to Q, so that would be from 1 to 3, and then again from, I guess that'd be, I'm going to say that that's ending at 9. Seems reasonable. It's not quite as far as that one, so I'll say from 8 to 9. It doesn't have a solid dot there, so I'm just going to put a curve. And I'm going to say now that the points of inflection or again, I'm going to call them POIs, R, P, Q, and R. Those are the points where the concavity changes direction. It goes from being a curve that has a minimum to a curve that has a maximum. Minimum, minimum, maximum. All right, let's do this with some numbers. Determine the concavity and the inflection point, or inflection points, there can be more than one, of y equals x cubed plus 3x squared minus 9x minus 8. Okay. All right, why don't I give you a sec, and you can try finding the derivative of that, and then find the second derivative of that. I'm going to open up Desmos over here. I can do that. Let's see. Oops. Let me get that out of your way. Sorry. Oops, you don't really want that in your way either. There we go. Okay. So find the derivative and the second derivative. I'll give you a second, then I'll catch up to you. Okay, let's see if I can catch up to you. So y primed is 3x squared plus 6x minus 9. And y primed is 6x plus 6. And we're going to use two facts here to help us out. We're going to say, of course, that the curve is concave upwards when f primed is positive. So we're going to take f primed and set it to be positive. So I'll divide both sides of the inequality by 6, and then I have x is greater than -1. So I can say, well, actually, maybe before I make any conclusions, let's also say that the curve is concave downward when f prime primed is less than 0. And algebraically, f prime primed is less than 0 isn't going to look a whole lot different. So there we go. So I can make a conclusion here. I can say, therefore, from those two facts, I can say that since the curve changes, from concave down to concave up at x equals -1, and I should maybe say moving left to right. Not that that really matters. Just gives me kind of a visual of the graph. I can say that, and I guess we could figure out what -1 run through here is. So that's -1 plus 3 is 2. 2 plus 9 is, 2 plus 9 is 11. 11 minus 8 is 3. So I can say that -1 comma 3 is a point of inflection. And it's a good thing that we have kind of an algebra way to solve that, to figure that out. Because let me show you this graph on Desmos. Let me just drag it over here. There we go. Notice it's not all that easy to see exactly where this graph changes from a curve that has a maximum to a curve that has a minimum. Where in here is that point exactly where it changes from the slopes are continually decreasing to they start to increase? That's actually kind of a tough ask. So it's a good thing we can just say that we can find it algebraically. It turns out it's this point exactly right here at -1, 3. And actually, I've stretched this, I've made this graph to kind of fit the grid here. I played with the settings a little. If I go back to the original settings, it's even harder to see where it was. Okay, so there we go. So there's our first example. You know what, though? I actually kind of, can I undo that change? No, that doesn't do anything. I'll have to do this the hard way. Okay, what did I change the settings to? I changed it from, I think the X is okay, but I think I made it from -15 to 20, I think. There we go. Okay, so before we leave this graph, let's reinforce the last couple of lessons. Notice that the point of inflection doesn't have anything whatsoever to do with that point there and that point there, which Desmos is nice enough to just give us. But let's make sure, let's run through the algebra again. How do we find that? Let's say, okay, I don't want to go on to the next page yet, so I'm going to move over. If you want, you could move on to loose leaf or something. I'm going to move over here and say, while we're at it, let's find max and min, right? We know it's a cubic. We are fairly sure that there could be a local maximum and a local minimum. So let's see if we can find that. Now remember, we find that by setting f primed of x to be 0, finding the places where the tangent is horizontal. So this was f primed of x, right? So I need to make sure I copied this right. That was right, wasn't it? Yeah. Divide both sides of the equation by 3. I think maybe we've seen this one before. This one seems pretty familiar. And that's going to give me critical values. Remember that? So this is acting as a bit of a review of previous day stuff. Critical values that happen when x is -3 and x is 1. Now, you might be wondering, okay, he's about to set up that interval chart. How come he didn't set up an interval chart when he was solving for this one? Well, I didn't bother with the interval chart because this thing is linear, right? It only has one factor, really. I mean, yes, it has a factor of 6, but that doesn't matter. Its only factor is x plus 1. Whereas over here, I have to deal with multiple factors, right? X plus 3 and x minus 1. So I think I would make my interval chart. So intervals, and then the first factor, the second factor, and then what's the entire function doing? And let's see, so okay, so our intervals. We can go from -infinity up to -3, so that means that's when x is less than -3. Then we can be between -3 and 1, and then we can be greater than 1. So there's our 3 intervals for this cubic. All right, pick a number less than -3. That's going to make this negative, this negative. A negative times a negative is positive. So over this interval, we are increasing. Pick a number between -3 and 1. I'll pick 0. 0 makes this factor positive and this factor negative, which makes it decreasing. Let's pick a number bigger than 1. How about 2? That makes this positive, which makes the function's product positive, which makes it increasing. So there we got it. So therefore, x equals -3 is a local max. And how do I know it's not an absolute max? Oh yeah, because it's a cubic. It's going to go up forever. There's no boundary on this function. So x equals -3 is a local max. Again, how did I know it's a maximum? Because as I approach -3 from the left, it's going up, but after I leave -3 going to the right, it's going down. So that makes -3 a maximum. And x equals 1, put another therefore on it, is a local minimum. And I know that because, again, it was decreasing approaching 1, but then increasing after 1. And you could then make a full conclusion, give me the exact point, go back to the original function, plug in -3, it'll get 19. So therefore, -3, 19 is the local max. And plug 1 into the function, the original function, and you get -13 is the local minimum. And that's pretty much what, I mean, that should be exactly, not pretty much, that should be exactly what Desmos shows me. And, yep, 19 and -13. So there we go. So now we have all kinds of new tools in our arsenal for how we could figure out what these graphs are. Figure out what they look like, right? The name of the unit is curve sketching. The other day somebody was asking, what happens when the curves are rational curves and you have denominators? Yeah, and I did point out, well, they get weird. And one of the things this unit is going to arm you with is the tools to actually explore that weirdness. So let's see if we can figure out the concavity and whether or not we have inflection points for a rational function. I'm honestly not 100% sure I know what that looks like. So we're kind of flying blind here and letting our algebra help us out. So f primed of x is, okay, so low d high minus high derivative low. That's a 4. Divided by denominator squared. Okay, let's simplify that out a bit. That's going to be 4x squared minus 2x squared minus 8 all over 4x squared. No, you can't cancel those 4x squareds, don't you dare. So that's going to be 2x squared minus 8 over 4x squared. And I can simplify out a 2, giving me x squared minus 4 over 2x squared. So there's f primed of x. What's f prime primed of x? All right, well, f prime primed of x is going to be, I'm going to have to take the derivative of this thing now. So again, it's low, d high, minus high, d low, all over low squared. That's a 2. All right, let's figure out what that looks like. That's going to be 4x cubed in the left side here, minus another 4x cubed, plus 16x, all divided by 4x to the 4. Well, those actually do cancel. So I'm looking at 16x over 4x to the 4, which I can simplify down to 4 over x cubed. So there we go. We have a first derivative, we have a second derivative. If I was looking for critical values, I'd be using the first derivative. I'm looking for concavity tests, so I'm doing the second derivative. And what do I know? I know that we are concave up when the second derivative is positive. No real algebra to be done here. This is just basic logic, right? 4 is a positive number. It would stay a positive when you divide by another positive number, so x has to be greater than 0, because when you cube a positive, it's still going to be positive. So therefore, I'm going to say, therefore, the function is concave up. I'm already tired of spelling the word concave. Are you okay with CU for concave up? From 0 to infinity. And this function is going to be concave down when that exact same thing, second derivative, is negative. And again, there's no point in doing an interval diagram for this one. It's a pretty easy one to just sort of reason out. 4 divided by what kind of a number would be less than 0? Well, then x cubed has to be negative, which means that x has to be negative. So therefore, f of x is concave down from negative infinity up to 0. Okay, what's happening at 0? Well, look at the original function. What can you tell me about x is 0? Oh, x can't be 0. You can't divide by 0. So f of 0 does not exist, right? It would in fact be a vertical asymptote. And remember Newton's law from our last chapter. So again, while we're at it, let's explore max and min. So again, let's tie the first couple lessons to this lesson. So let's explore max and min. We know that the critical value of x equals 0 can't be a local max or local min because it doesn't exist there. So we'll have to look for other critical points, and the other critical points happen when the slope is 0. So the first derivative, the slope, was x squared minus 4 over 2x squared times both sides of the equation by 2x squared. Resist the temptation to move the 4 to the other side. Think factoring. Factoring is always the easier way to do it. And again, since I've got 2 factors, I think I'll go back to an interval diagram or interval chart. X plus 2, x minus 2, and my function. Okay, so this would be x is negative 2, this would be x is 2. But remember, I do have kind of another interval that I have to deal with. I have also x is 0. Kind of breaks things up, right? Excuse me. So let's see. So how about we'll start with the interval from x is less than negative 2. So let's see, at negative 2, so smaller than negative 2, I'll try negative 3, negative, negative, positive, increasing. Let's go now between negative 2 and that critical value that ends up not even existing, but I know it's a critical value, so I should explore it. What happens when I'm between negative 2 and 0? Well, pick a number between negative 2 and 0. How about negative 1? Negative 1 makes that a positive, makes that a negative, so that's a negative, so we're decreasing. Right? right? So let's see, negative 1 makes that a positive, negative 1 makes that a negative. Yep, okay. Then let's try between 0 and 2. And let's see, so between 0 and 2, so how about 1? 1 would be a good number. 1 would make this a positive, and it would make that a negative, which is still, still negative, which is still decreasing. And then we would say, what happens when x is bigger than 2? And that makes everybody positive, so we're increasing again. And notice the algebra is telling us what we kind of knew from the fact that x is 0 doesn't really exist. It's an asymptote. There is no change in the behavior of the function as you cross past the critical value of 0. Therefore, it is not a maximum or a minimum, which makes sense because it doesn't exist in the first place. But it's nice that the algebra tells us that, or the calculus, I guess, tells us that. So I think my conclusion will actually be, therefore, negative 2, at negative 2 we switch from increasing to decreasing. So if you're increasing then decreasing, that's a maximum. And it's a maximum, okay, what was the function again? I gotta go way back to the, oh, hang on. I'll just look it off the page here. So, oh, there we go. So if I plug in negative 2, oh, I get negative 2. So negative 2 is a local max. And then these guys here, it changes from decreasing to increasing. So 2, do the math, 2 is a local min. So there we go. There's what I know about this graph. I know all kinds of things about this graph now. I know that it's concave up anytime I'm bigger than 0, so it's curving up. So I have a graph where, let's make a quick sketch. I have a graph where it can't touch the y-axis, that's an asymptote. It has a local max of negative 2, negative 2. So that's a local maximum, but then it's kind of curving down. And it has a local minimum of 2, 2. And it's curving up on that side. So I think it's going to look something like that, or some sort of curve like that. I know that you approach asymptotes, right? So I know it has to kind of get closer that way. So I think it's going to do something, I don't know, something kind of like that. So let's see. Let's look at Desmos and see if it agrees with me. Okay, so let's get rid of you. You've done your job. And yeah, there it is. Very cool. Okay. So let's see, where were those points again? Local max, or local, there we go, local min, and there we go. As soon as you click that you're looking for them, Desmos usually finds them for you. And there we have it. That's basically it for today's lesson on concavity, and a little bit of a chance to review max and min. We'll do some more examples tomorrow. We'll stick with this this part of the section of the unit on concave up, concave down. But if you're ready to get started on some homework, if you're caught up on all the other assignments right now, hang on, I haven't opened the blog yet. I did put some questions on the blog, but you don't have to have them done for tomorrow because we're going to be doing some more new examples tomorrow. So there we go. So if you're ready to start working on concavity and points of inflection, it's numbers 1 to 3 on 5.3. We're skipping around in the book a little bit. We're going to change the order that the book's in, so we jump to page 10. And if you're looking to print out tomorrow, or I guess it'll be Thursdays, because we're going to do some more of these examples tomorrow. So this will be Thursday's lesson. Okay? So there we go. I'm going to stop my video. Thanks for watching it, whoever watched it.